All right, so I'm attempting to give a little tutorial today as I was asked on robust design optimization. Bear with me, this is my first trial at this. So, if you spot any mistakes on the slides, please let me know during or after. I'll try to take notes. Hope they're clean. And then I really want to acknowledge that my postdoc Yulin has helped quite a bit, as his research area is also in RDO with creating this material. And of course, thanks for the organizer for bringing this together. It's really nice. I think I fall into the category of people working on methods. I have not worked explicitly on plasma fusion, in that sense, on fusion reactors, fusion design. So all of the examples I will have here will be with different dynamical systems that also have uncertainties, that also have transient dynamics. And hopefully we can make that jump to see where some of these methods could be useful. What I thought would be helpful is in design, actually, what matters a lot is what you want to design for. And so I want to spend quite a bit of time. I should have also added these like time buttons that Tim and John had yesterday. They're fantastic. So I want to spend about 20 minutes, maybe 15, 20 minutes on problem formulations. How could you design? What is an objective for you? Then I'd like to spend a little bit of time on some solution methods. None of this will be overly comprehensive in the because of limited time. And then in the theme of this workshop and long program, I wanted to focus specifically on multi-fidelity approaches that are out there. And some of them will literally mirror what we have seen yesterday in forward UQ from John. And then some examples at the end. At any point, if you have questions, clarifications, or anything, just feel free to interrupt me. Okay, so this is the one slide where I have no expertise, but I try to do the best to synthesize from what I read, what's been said in this workshop, and I will let all the plasma fusion experts, fill out the rest of the bullet, and we could make it interactive, and then I would never get to another slide, I guess. That could also be this is actually my last slide. Anyways, things I've heard, of course, we have the models and we have the parameters and we have uncertainties in both of them. I'm not talking much about uncertainties in measurements because I'm not dealing necessarily with inverse problems, but we also have those, and we heard that from Tim. We have stochastic models for turbulence and transport. We have these, we can model them as either deterministic solvers, but we have seen PIC solvers, of course, also have stochasticity, and even all the turbulence modeling inherently is a stochastic process. We have the model particle collisions in kinetic codes, often done also via Monte Carlo approaches. The fusion reactions, you have to give cross sections, and those are really just probabilities that you state for fusion reactions to occur. And then we just heard from Jaime all the things about fusion materials, wall interactions. It was pretty clear that there's a lot of things we don't know. So I think we can just put them all in the envelope of material properties, damage, irradiation damage, erosion, bubbling, and other things. So a lot of things in the material side as well. Then as Frank mentioned, two things. The known unknowns, so other things that I did not know, but maybe Frank could fill that out, and other people. But then there's also the things that maybe the community hasn't discovered yet for lack of specific, experiments or things where things haven't been quite observed yet. And those are often the scary ones, right? Like, what do you do with those? You can always try to lump things, aggregate things, but it also means that we have to have the right data where these aggregate things would be seen. Anyway, so we have these uncertainties. I think that became clear also yesterday in the two tutorials, and forward and inverse UQ. This tutorial is about design. So now, design is an optimization problem. I wanted to start with the simplest thing, which is the deterministic design, which is an optimization problem that most people have solved in some way, shape, or form at some point. The idea is you minimize a cost function, and this cost function we're going to call J of D throughout the talk. There'll be a little bit of an overload of notation here, but I'll get to this and I'll disclaim it in a few slides. Really, this function is a function of the design parameters, if this is the only thing I have, But implicitly, of course, design parameters influence your quantity of interest, so it's really a function of the quantity of interest. And then you can have some constraints. So here you can have multiple constraints. They're all grouped into this G vector. And again, these constraints usually could depend on other quantities of interest. There's quantity of interest that you want to maximize or minimize, and quantity of interest that you need to keep track of for constraints. Everything is written so simple that it looks actually pretty simple. Your design variables, once again, excuse my ignorance here, but I saw that, for example, in stellarators, geometric parameters, the stellarator geometry itself, the 3D curvature and manifolds you're trying to span, coil parameters, other materials, anything you want to think of. Think of what you would like to design and think of what these variables would be. Often, of course, they could be quite high dimensional, right? So those are vectors. We constrain them to be in some set of design parameters. That doesn't have to be an interval bound. It doesn't have to be a box, but oftentimes people pick boxes. They like lower and upper bounds, okay? So these type of box constraints are pretty common, but that's not what we have to be. I wrote it throughout the tutorial in a more general form where D is in some specific, some more general set D. Okay. Then we have a quantity of interest. Once again, for example, this could be the plasma current. Frank showed a few of these quantities that maybe someone who sits in a monitoring room, or what do you call them, is tracking currents, volume, stored energy, internal inductance, other things. Those might be things you want to minimize or maximize, depending on how you choose the cost function. Constraints, all kinds of things you could loop in there, and of course you have a cost function itself that you're trying to minimize. That is a function of the quantity of interest, or maybe of a few quantities of interest. Okay, so that's the deterministic problem. That's not what this tutorial is about. Then robust design came ever since people started doing serious manufacturing and measurements and really cared about tolerances. So Taguchi out of Japan is largely credited with bringing up this new idea of robust design, where we want to distinguish about designable factors, they call them control factors, but things that we can design for and things that we cannot necessarily, things that we can really affect, these are the design variables, and uncontrollable noise factors are kind of our random variables. So there's a split in philosophically came up in Taguchi's method, and then of course it's much more formalized than the things that we're talking about today. And so instead of controlling noises and saying, well, this system can only take this much or that much, or tightening tolerances, the idea was of Taguchi to make the system robust. So it's actually insensitive to some extent to these noises and external disturbances. I know yesterday Tim talked about design of experiment, and there's very simple ways to do this, and of course the current state of the art is much more advanced. Here this was not like in a data assimilation setting where you said, I'm trying to find a new experiment, so I maximize my KL divergence and I'm trying to learn something new. This was literally about, if I had to run a few experiments to build my model, which would be the right one. And therefore, Taguchi introduced these orthogonal arrays, which are very simple lookup tables that say, hey, if you have that many parameters, and your parameters could be subdivided in so many small subintervals, then you should choose a certain, what they call an array, okay? But the key idea is between, actually, I found this interesting in preparing, read a little bit into the history. The American philosophy was this one, and this was the Japanese philosophy. So the American philosophy said, a part is good, it's made to a spec, and a plus or minus sigma, or how many sigmas. The moment a part deviates from that, we're going to call it bad. So binary decision. Parts have to fit tolerances in cars and in rockets and in other things. Taguchi said, well, from a customer perspective, this is actually not fully true, and hypothesized that a part could be, locally the quality degrades as you're not hitting the specs, right? But the part is not immediately, this all came from manufacturing, the part's not immediately bad, it just means it has a lower quality. Maybe a customer is willing to pay a little bit of a lower price still. But eventually, once you totally miss the spec, then you're off and we're going to call it back. So the idea of this more quadratic cost, which is called the Taguchi loss function, is very key to the notion of understanding robustness. That locally you can still be good. And there was mentioning of signal-to-noise ratios and other things. But it's a nice starting point for where all this robust design is going to. So this was philosophical more and somewhat technical. But really it becomes more technical when we start thinking about the field, the mathematical field of an engineering field of robust design optimization, which is now the formalism. We're again trying to minimize now. So we're measuring robustness in this case by a cost function. So I'll have a lot of J's here. They sometimes do a little bit of different things, but they generally the cost function, where I have a cost function that has two objectives. It is a function of the mean, which is my mean spec that I want to hit, but also a function of the standard deviation, like how far I'm off. Again, my random variables, so now I introduce random variables. I don't just have a design parameter, but there's these, he says, uncontrollable noises, right? So I have a vector of design of random variables, and R of them. They're usually given by or defined through densities. If you want them and you don't know anything else, you could just choose them to be normal, but they could have any distribution. Okay. And then we still continue to have constraints. The constraints are, of course, also to some extent having to deal with uncertainties, and there's a big question of how you do this. We'll talk about other design strategies. But what you see is there's a multi-objective optimization problem where we're trying to reduce the mean and the variance at the same time. Okay, so we would like to get a mean where we think of like a loss. Oftentimes, this is why we know the mean. The reason it's minimized is because you set up the problem so that the minimum is like the best thing you would like to have. Okay, but then the variance also you want to tighten so you have a very good product, or design or fusion reactor, you name it. Okay, so this often deals in practice that we have to identify Pareto optimal solutions to characterize exactly that trade-off. So that's the most general form of writing down this RDO problem. Now, what most people do is you turn the multi-objective into a single objective by assigning basically this linear combination of the two things you want to do. So now you need some weights in order for this to make sense. So you're taking this multi-objective, you need a weight W1 and you need a weight W2, and you have your expectation and your variance. So now you get to decide what you want to put more weight in. You usually start with a 50-50, and then you can tune. And you'll see, depending on, if you have massive variances, that's more important for you to drive down. You can do a 20-80. But there's quite a bit of heuristic and design experience required to choose these two weights. All they have to do is to sum up to 1. Okay, the problem is you've turned this multi-objective into a single objective. Now you're only finding solutions that are on the convex portion of the Pareto front, so you're not solving the same problem anymore. And you also don't know if that you can actually find a solution on the Pareto front to the original problem. Nevertheless, this is simple because now you have a scalar cost function, and it's relatively easy to implement.
So can I ask a question?
Yes.
How would you interpret if W1 was 0?
Oh, then you just do if W1
what I'm saying is that I'm not sure if there are some additional constraints on the weight, because it seems to me that if W1 was 0, I'm not sure what you would be trying to minimize.
That's a good point. I mean, we probably want to put them, make them larger than 1. Yeah. I guess, I wonder if you ever have a situation where, if someone can think of this, if you ever have a situation where you don't care what the mean performance is, as long as you know it very well. No. Yeah. No, my beautiful iPad, where is it? I'll write this here so we kind of all have it. Okay, it isn't.
can often not formulate that as a constraint problem, right?
Right.
Mm-hmm. Okay, so good point. We're going to go with positive weights. Strictly positive, so we don't have this situation. And then, of course, the main point I was trying to make, you have an easier problem, and this is what most people do, and then they play around, and you can show results for certain different weights. This is just a formulation. So in part one of the talk, I just want to talk about formulations. Like, this is a problem you could formulate. If that's what you want to solve, you're kind of good.
So have people ever changed that and used other ways to do multi-objective optimization?
There's many of them. I actually
So
chose...
this is just one out of...
This is just one of them. Yeah. So I have like 4 different methods to approach this problem, but I threw them in the backup slides because they're getting really technical and kind of heuristic how you do this. Yeah. You can do many different ways of doing this. Yeah.
And you have shown this for simplicity, or,
Yes,
or
yeah.
is this the most...
Oh, this is
common?
I mean, it is kind of the most common way to do this, at least what I have seen in my area of like, I've seen a lot of work in structural engineering, aircraft design. This is one way that many people do it. I don't know. People working in UQ would kind of agree or not. Well, there's many... Okay, Tim approves. No, it's the most common way for simplicity, but you can do many other ways, and I have actually, I'll post the slides, and there's a bunch of stuff in the backup. Maybe we get to it to discuss those. Because now when you have multi-objective, multiple constraints, I mean, you got to work with like choosing different optimizers that do that and interpret the results correctly. Okay. The one thing I've been fully hiding here is like everyone's been talking about solving differential equations, whether ordinary or partial. I do want to highlight that our cost functions look very simple, and this is actually one of the reasons we need multi-fidelity methods, right? If I write down a cost or a quantity of interest of a design in a random variable, it really means I chose a design. So I choose, for example, a material for my tokamak wall, and I have randomness that I have associated with it. I usually have to solve equations, right, differential equations or other types of equations in order to get a state of the system, the plasma state or other things, and then ultimately all of that loops into, I measure my quantity of interest of that state. So when I write this, I don't mean that I have very simple models, it just means it makes my notation a little bit easier, right? And now you, of course, we have all the problems because when we want to do this type of stuff, oftentimes other things like multi-fidelity approaches that actually want to reduce or give me an approximation of that state. Then also need to account that that state actually depends on variables and parameters, and that becomes certainly very tricky. As John pointed out yesterday, surrogate modeling in high dimensions for the purpose of UQ is definitely not easy. Okay. But I just wanted to point this out, and some people even look at this as a setting of how to formulate control problems. So the general approach to solving these RDO problems, just want to highlight this, is you first need to spend a lot of time, and this will be one of my key takeaways, on the modeling part. To understand what your variables are, what are the things you actually can design, what are your objectives, multi-objective, single objective. I'll show you a few other objectives in a bit. What are your constraints? Do you need all of these? Because you can always add a lot of stuff, but you're getting to a point where maybe you don't even have feasibility, right? And then the uncertainty modeling. Identify the parameters, the model form uncertainties, other things that you have, and potentially, if you can, parameterize them. That's a nice way. So you start with your system modeling. All the plasma people I've seen here understand system modeling very well. Then you peel them out again and say, well, what if that is uncertain? Then you need to find a way to propagate uncertainties in the absolute brute force way is just sample these parameters and run a solution, but you could do this multi-fidelity. And then you do some initialization. You find a proper optimization algorithm that will depend on what objective you choose, right? And then you do inside a double loop, because in every optimization you have to deal with the random variables. So you have to compute expectations and means, expectations and variances and possibly other things. and that is expensive. And so inside the loops, you're going to have to deal with more calls to your models. Okay, and once you're done, you can claim success, and you say that you have a robust, optimal solution or design that satisfies your requirements. Okay. Again, robustness in the way that the robust design optimization literature is talking about usually just requires the mean and the variance. There's also design under uncertainty or optimization under uncertainty where you can do a lot of other things. It's just terminology, okay? All right, so that's your general diagram. Then you have a second framework to deal with things, or another one. This is called reliability-based design. So in robust design, you put the uncertainty, you want to design so that the quantity of interest or your cost function has minimal variability and drives you to an optimum in the mean. In reliable designs, you're trying to minimize the cost, but you really care about the constraint violations. So if you have hard constraints and you say, that wall cannot be hotter than X, or at the core we can't have more impurity than Y, or something like this, then you should put it into a constraint. Now the problem is these constraints are not deterministic anymore. Due to the presence of the random variable, you need a probabilistic, you need a measure somewhere on the constraints, and what people in reliability talk about is that they just count. They count the probability of constraint violations. Probability that this is now called a limit state function, so overloading G notation a bit. Before it was just an arbitrary constraint, and now in that literature it's called a limit state, and it's usually a scalar function, and it defines what you call as like the limit the system should hit, and everything above that would be failure, everything below that would be success. So RBDO by itself is a binary, reliability is a binary decision. You're either reliable or you're not, okay? And it's counting zeros and ones basically once we evaluate this. I'll show you how this works. Again, it's a single objective problem, and you can specify how much deviation from your constraints you can allow. You could say, hey, I'm fine if we're going to miss 0.01%. In 0.01%, this wall gets a little bit hotter. That's fine for our material. Some people choose that threshold to be 10 to the minus 9, right? I mean, it's really a design thing, and choosing that will very, very much determine how good your optimization runs. In terms of like running into feasible sets and other things. But the key is you have this outer and inner loop, and that is a problem in these problems because it just makes everything more expensive. Outer loop, you optimize over D. Inner loop, you have to compute at any given D, you have to compute the probability under the uncertainty coming from your random variables that your constraints are violated. And that also requires you, usually in the most brute force way, to evaluate your model again. Any questions so far? Yes?
So in the beginning,
You looked like you had a question. That's why I was actually stopping. Yeah.
In the beginning, you had the American and Japanese.
Yeah.
Are you saying that if you want to be Japanese about it, you put it in the objective function? If you want to be American about it, you put it in the constraint?
That's a good analogy. I don't want to make any specific. I don't want to take any.
It's just
This American and Japanese came up in the context of Taguchi, who was Japanese, and there were some other gurus at the time in safe quality manufacturing in the U.S. that were pitching for one versus the other. Now that we've entered the world of design optimization, we're a very coherent community. We wouldn't distinguish along those lines anymore. Yeah.
But in terms of those pictures, it's
no, actually, I don't think this applies here because this was all in like quality manufacturing and Taguchi's methods. Here we're literally in like the history of optimization now, of where you put constraint. And I don't think one of them is associated with the Japanese school of thinking, and the other one is associated with the American school of thinking. Yeah, at least not that I am aware historically. Reliability-based design has been around for a while.
But it feels like I guess what I'm asking is, it feels like the constraint is saying yes or no.
Yes. Okay. Yeah.
Then,
that analogy holds true, of course.
Okay.
Yeah. And I'm trying to convince you that this is not the best way.
Okay.
In a second. Okay. It is a binary constraint, exactly like that box function, right? Either I'm going to throw the part away or I'm not going to throw away. But Yeah, and it's very susceptible by how you define this G, like very sensitive to that. So if you say, hey, the wall should not be hotter than 2000, it's one thing. Do you really know that? Is it 1990 or is it 2100? Like oftentimes people make like these heuristic choices, like let's just pick that. But that'll certainly affect your feasible regions and everything else. So there's quite a bit of uncertainty in like how you choose these, because the moment you choose a threshold or you define your limit state function, you're boxed into that, to the binary decision. And by the way, binary things are never great in optimization. So that's another thing.
Well,
Yes.
that objective function you have, again, you got rid of the variance. You're now saying that you want to only optimize for the expectation value of that. But then it could have your design which you choose. Say if you do it 20 times, you might get a huge variance, right?
Right. This is what's known as RBDO, is that formulation. Been around for 50, 60 years. So I'm just showing you that. You can do mix and match. I mean, this is the main point. It's actually good we're having this discussion, because you're the one who decides what you design for. I'll have another slide on this that puts a few of them together, okay? But then you also are in charge of figuring out which optimization algorithm you need to choose and which surrogates you probably need. We'll talk about this, right? Okay, so then there's this business of, we can pitch this one level further. You can also use things that have been kind of popular for the came out of the finance community in the last about 25 years ago and started making it into engineering about 15 years ago. So you can use these risk measures. And John needs to hold on to his seat now because there's a few things that I'm saying loosely. So I'm not going to go axiomatic in any stuff here. But okay, so we're doing risk measures. You can read more about these by books, for example, by Shapiro. So where I didn't do anything other than just calling something R that I had called J before, but I'll tell you what. So in RDO, the risk, so when people talk about risk, there's the colloquial term of risk, and there's a mathematical definition of coherent risk. It has a few axioms, and a risk measure, if you satisfy all the axioms, then you can call yourself a coherent risk. Otherwise, you're just a risk in the colloquial term. So when people talk about risk, we just have to be careful about what they really mean. Some people say, well, the mean can be a risk measure. They use that in presentations. Problem is you have no information about deviation. You just maximize for or minimize for mean performance. Oftentimes the variance is important, so you can do mean plus variance, which we have seen is also an RDO sorry, I wrote RDO problem here, but in RBDO, this is the optimization, and we have a probabilistic constraint. You can do mean plus variance. The problem actually is when you do mean plus variance, like we do in RDO, okay, here, you're actually, so it depends what your cost function is, but you're penalizing a cost that is above and below, right? So say your cost is dollars, how much does it cost me to build the next generation F-35 or the next nuclear reactor or a fusion reactor? I don't think you care about if you come in lower in the cost, right? So what you penalize, you want to drive the mean cost down and all variance that's above that mean cost, right? But not below. So, so then people said, you know what, we can actually just make this the mean plus the upper semi-deviation, which is everything's above the mean I want to penalize in my risk or in my cost function. And that's not bad, just that there's a little bit of this is still not nice to optimize. And then these people came around in around 2000 in the finance community and said, we're going to define two different words, and I'll stick with these words, but they're, you can call them average value at risk and other things. But we have something in the next slide becomes clear. There's a value at risk that is basically a quantile. So you choose a level, say 95%, and then at that 95% of the CDF, you go over and you find your quantile level. I'll have a plot on this on the next slide. And the conditional value at risk really says, I'm going to take my quantile and integrate everything that's above this value of my quantile, which then becomes a tail integral. I'll have graphics about this. The problem, anytime you compute tail integrals, you have all kinds of issues because you introduce the same as in the upper sigma deviation, nonlinearities in the cost function. And really what you need to do is a clever way to evaluate a tail. And that usually boils down to using some trick, whether that's importance sampling, maybe paired with control variates even, or surrogates.
So are you trying to, in that, go back to the previous slide?
Yes. I think this one is easy, actually, but we can go to the previous one.
So is the goal over here to try and not get to the tails?
Yeah. Yeah. Actually, I have 2 slides, and then I'll take your question again. So first, I want to just show this histogram. This would be a standard histogram of a quantity of interest. You run an experiment. Here's your mean. Ends up you having quite a long tail. They were looking at this as a function for portfolios and stuff, so you can think of this as a loss, but you can also think of it as a max pressure, as a max temperature, as whatever you want to think of it as an engineering quantity. And so what you have is usually here, that's that maximum loss. That's the worst case scenario that could happen. That's like probably Frank's worst nightmare and ELM happening every microsecond, or like something bad happening all the time. That's the worst, that just shuts down everything. When you design for the maximum loss, you're extremely pessimistic, and you're probably not even turning on the power, right? So you need to find a little bit of a compromise. People designing for means, of course, are missing all of this stuff. You're shifting it. You can have distributions that have identical means, but could be horribly exposed to tail events. So again, var, the value at risk would be here, and the C-var is really the integral of that quantity, of like from the var going out to the maximum loss. And here the CDF plot is best shown. You have your cumulative distribution function. You pick a level, I think this was 0.9, 0.95 here, and this is your value at risk at this level beta 2. This is the value at risk at your level beta 1. And then these two would have differently associated conditional value at risks, would be over here and over here, because they're different, you chose different levels, and this is basically what you get. I have another slide that I want to show you, and then we can return to this. So let's focus just on the on the densities here. So these are the PDFs. You can have 2 different scenarios where you have a value at risk and then your conditional value at risk. You chose the level beta. So you could have, for example, an output quantity that has kind of a short tail, where C-var and var are close to each other. It's kind of indicative of a short tail. But you can also have a longer tail, where C-var is a little bit more to the right. So in a sense, if you're minimizing for that C-var, you can either, here I stuck it into a constraint, because you could say, hey, I really don't want these tail events to happen too often, right? So can we cap those? You can put them into the constraint and get into a feasible region that way, or you can minimize it in the cost function, right? But basically you're shaping, by pushing the C-var a certain way, you're shaping the distribution, right? Now, the great thing about this is it has nice mathematical properties. We're not talking about this today. There's really nice work. John's done work on this. The original papers of Rockefeller. Johannes Royset has done a lot of work on this. There's a lot of nice work you can read up on the mathematical properties of this and how it's been leveraged and exploited in optimization. From an engineering perspective, you don't need to choose necessarily a failure. You don't need to choose a failure threshold anymore. Before, you had to design your limit state function that said, if I'm going to be over a certain threshold, I'm going to be failed or I'm not going to be failed, like binary decisions. We don't have to make that decision anymore. All we say is like, I want to minimize the 5% worst outcomes. I want the average of the 5% worst outcomes to be minimized if you choose it in the cost function. Or you constrain it in a constraint, okay? So in a sense, all you have to choose is like, what do you want this beta to be? And mostly this beta is, anywhere between, 5%, 1%-ish in that range. And really, the key thing here is in a binary decision of saying I fail or I don't fail, I never tell you how bad I fail, right? I'm going to be very close to a threshold, a degree off or a degree off here. But in failure probabilities, they both count the same. A failed sample is a failed sample. A failed experiment is a failed experiment. But you could have failed by 80% or you could have failed by 1%. And I would argue that one of them should be weighted heavier than the other one. And therefore, in CVAR, since you're computing a tail integral, you have to take into account the value of the quantity of interest. You don't just have to count, you have to take into account the value of the quantity of interest. And therefore, I think it's a really nice way to use these in design optimization. Yes, Chris?
So maybe building on this, maybe you touch this later, like, the way I might think about this for, say, a reactor or something, is, there's like, your temperature, like, if my wall gets a couple degrees hotter or something that I want, then, okay, that's bad. If it gets a bit hotter,
right,
then maybe I have to shut down operations for, an hour or a day or something. But if it gets way above it, then I have material damage.
Yep.
With like that sort of cost of increasing fit, like if that was my if I'm optimizing.
Yeah.
Would that be in how I pick beta, or is that going to come in separately, like
Yeah. So beta implicitly informs what your value at risk will be, and that value at risk will be a temperature, basically, and it'll turn out, depending on how you choose your beta, it'll be, let's say x or 1.1x or 1.2x. So you'll have to figure this out a little bit if that's acceptable with you. But in general, you would minimize, if you want to be more conservative, you could say choose beta to be 0.1.
Recording in progress.
So 10%, you track your 10% worst cases. But what you just explained, it will penalize the one that just barely failed, just a little bit, but it'll certainly penalize the simulation outcome that would have resulted in a terrible condition much, much more, right? By the way, you should have actually raised this hand. I want someone to raise his hand, and Chris said he was going to do it. Yes. Yeah, please add, John. You have, yeah.
There's a real nice, Boris doesn't have the time to get into this, and Boris has mentioned other people's names, but not his own. He knows all this stuff, Taguchi. So there's a connection between utility or disutility theory and how to elicit these types of risk measures. And this is really formalized nicely mathematically. So if you think about like risk regret, you can think about it, say a linear function was CVAR. Like I have no regret if it's up to a certain value, it's flat, and then I have a regret that goes linearly up like this. And depending on the value of beta, essentially determines the slope of how much I regret increasing larger values of whatever quantity I care about. And so there's some really nice theory about that. That's one of the great things about this. You could speak to a stakeholder and just elicit this regret function, and then you can turn that into a risk measure and do all the optimization.
Fantastic. Yeah, there's a nice paper, the risk quadrangle, right? That came out like, I don't know, 2008 or so.
The funny thing that the people that popularized this call CVAR different things. The same people on that original paper. One calls it AVAR, the other one calls it CVAR. It's very confusing.
But anyways, this really just historically, this came out of the finance community. These people were all advising basically hedge funds to figure out how are we not going bankrupt? Like, what's the bets we can make so we're not basically having to shut down? We can take a little loss, we can write it off for 5 years, and we'll still be alive, financially. But it has so many analogies to engineering, right, that people eventually discovered, and I think there's some beauty to that. Okay, haven't really made it that far. Okay, so deterministic, now I have everything here, and the mix and match, you pick your recipe, you want to design. So deterministic optimization, we minimize the cost, have a constraint. We can then introduce in RDO, we can multi-objective, we can introduce, means and standard deviations. We can also minimize CVAR, for example, or any other risk measure there's other things, there's buffered probabilities and so many things, but I just wanted to show you one of them. And then you can mix and match with constraints. You could say, hey, my constraint should be, I'm counting zeros and one, failure or not failure, or my constraint should be a little bit more motivated, like we said. I want to heavily penalize large failures and others. And that's exactly how you do it. Okay, but when you do this mix and match, some of the methods might go out the door. For specific combinations of the RBDO problem, we have nice methods to solve them. For other ones, you may have to rely on general purpose optimizers or design your own strategies, right? Okay. And really, some of the books I looked here is some of the material I used is this one, Wave U, Design Under Uncertainty, by Kim Martins, who's an MDO person, but has a nice chapter in RDO, and then a few papers from us if you're interested. Okay. So the reason I spend so much time, and it's been good that you guys ask questions, is it really affects what you design for if you chose the wrong function. We'll talk a little bit about solution methods. Of course, the first thing that comes into mind is like, anytime I have to compute a mean or variance, I'll use standard Monte Carlo. It's a crime that has no penalty yet. You know, you can do this, but it'll just cost you more time. So of course, you can just do approximations. You can run your model all the time for a certain design, and now a collection of random variables. That's the key thing. In the inner analysis, you have to run n samples of your model, n model evaluations, and you can do variance. Nice thing is people use this maybe to get a first sense on simpler models to kind of start implementing this, and this is usually the module you then swap out and use something more sophisticated. Okay. So John touched on this a little bit yesterday, and there would be so much to talk about how you estimate probabilities. I mean, you could actually teach a class about this. But the standard way in RBDO is to think about, we have two things here. Monte Carlo would be on the, our Monte Carlo for RBDO is yet you need this thing called an indicator function. An indicator function counts zeros and ones, and all you do is you run your model and you say, did it give me a 0 or a 1, right? And then you count the zeros and the ones, and that gives you the failure probability. As you can imagine, if you want a failure probability to below 10 to the minus 5, 10 to the minus 6, you need a lot of numbers to be statistically significant and converge, right? So that's usually out the door. Then you can dig into the bag of variance reductions. We heard control variance yesterday. I'm not going to cover these here. You can do importance sampling. And importance sampling is a nice, beautiful theory. Basically, you shift your distribution, or your density from which you pick samples to a certain region. So say you have your original density is sitting over here somewhere. This is the original. But you say, you know what? Things that actually fail are kind of over here. I'm noticing that I'm drawing samples from this distribution. I've already drawn 100,000 of them, and 3 of them happen to be over here. And those are the ones that told me that my system was failing. So now you're like, wait a minute, I should really be sampling from this place. How about I just sample from around here? Well, now I'm doing really great because almost every sample I'm hitting here is giving me a failure. But I have to account for the fact that I changed the probability density, right? And so importance sampling is exactly doing this. Now you have to do a reweighting. You have to say, well, yes, you're right. Your system failed in all of these cases, but you have to assign a very small weight to that failure because your original density is over here. Okay? But it gives you more failures and it lets you converge, get the variance down quicker. So that's a really nice way, and you can do this in multi-fidelity strategies pretty beautifully. It's a total art to find the right importance density. And then there's a pretty nice field of subset simulations, which uses like smaller and smaller subsets in which you can simulate things. Nested subsets also has a little bit of a notion of like a multi-level Monte Carlo setting. You can also look at this. It's pretty subset simulation is what I would say 80% of the people use in RBDO in the engineering community. Okay. Then you can do other things. So this is all specific to this RBDO problem. You have your constraint, your cost function to be the mean, and your constraint to be the probability of failure. If that is true, there's a method that was developed. If you start mixing and matching, you can't use that method anymore. But they call them also very popularly first-order reliability methods and second-order reliability methods. And the idea is once again relying on a change of measure. So you have your original random variable z, and you do a transformation to get you into standard normal space, which is this one with the radial coordinates, the radial limit sets. And then in this standard normal space, you have to transform your original lowercase g into the uppercase g, so the transformed failure region. And then really, to not dive too much into it, but you're now looking at the point that's closest to the origin on that set g of d and u, so this is your black curve. And the distance to that, minus the distance of that is your failure probability. Okay, just believe me, I'm not going to go into the derivation, but you nicely identify now safe sets and unsafe sets, and your failure probability comes out from this. Now, of course, this works beautifully if your constraint was already linear. You get an exact representation. If it's not, but it's reasonably, it doesn't have too much curvature, it's still okay, but that's why it's called first order. You can do second order, where you actually fit also Hessian information to the maximum a posterior point, and then you kind of get this second order curvature, and you would compute your failure probability with a second order reliability method by using a little bit of more complicated formula. But the idea is pretty simple in both cases, and it's widely used in the structural engineering community a lot. You do this transformation, this change of measure, and then you just solve this minimization problem, and you're basically done. That's one way to get. So we've now seen Monte Carlo brute force. Important sampling is another way, a Monte Carlo method. Here, it's a little bit of a detour to the problem. It uses a lot of approximations. And I think that's a good time to say, why don't we bring in some other fidelities, to maybe speed up Monte Carlo stuff. Any questions so far?
So that last one, would that qualify as like a variational method, like in the same way that we did Laplace approximation for estimating uncertainties? You're like essentially...
I can't answer this right now, to be honest with you. I don't, it really is just, it's actually a simple approximation, just a transformed space, either with a straight line or a parabola. I'm not sure if it has a variational equivalent.
I would call it that. Variational inference typically refers to minimize this layout divergence between distributions. Yeah. I think Boris is more right. It's sort of more just like an approximation of the failure region.
Yeah.
And a good question that someone might want to ask is, what happens when this is a multimodal failure region?
Yeah.
So it has the same kind of issues as variational inference. There definitely are strong analogies in that sense, but just people probably wouldn't call it that.
Right, yeah. Okay, so in the multi-fidelity world, so surrogate modeling, one of the nice ones, and we've actually seen this yesterday as well, is if you train a surrogate, you can, so PCEs are very nice for many reasons. I think, Frank, you had one PCE on your slide and the work with Yonne, the 14-dimensional. Was it a PCE or a GP? PCE, right? Yeah, okay. So there's variations of PCE, but the standard PCE basically says, so you usually train them on low-dimensional things. You're not necessarily training a PCE on the solution field of a PDE. You would have to do some KL. You would have to do some other things first, some modal expansions. But you can train them nicely on the parameter maps if the parameters are reasonably low-dimensional. So if your quantity of interest, depends on, a handful of parameters here, maybe, 5 or 8, and you have some design parameters, you can kind of like split this up so you write out a PCE into these orthogonal polynomials, and you have your coefficients. This is exact, of course, with an infinite limit for square integrable functions. You have nice orthogonality measured by the expectation of these two basis functions having, as it's written here. So that's nice. Of course, you always have to truncate the thing. So we're truncating the PCE at NP, arbitrary. You have to choose what level you want to do. And then you estimate, basically, what these basis functions are. So depending on what your distribution is of these random variable C's, let's say you have Gaussian, you chose Gaussian on 0, like Gaussian, zero-centered, then you would take Hermite bases. If you have uniform, then you would take Legendre bases. So basically, you know the basis. since you know the basis, you can now play a regression game to figure these out. That's what makes PCE so nice. Of course, that's the very standard PCE I'm showing here. In high dimensions, you have to sparsify that thing somehow, because also the PCE coefficients will blow up. You'll need a lot of cross terms, and it's not clear. We heard this also yesterday, you know, which interactions you need. You'd like to have low order interactions versus very high order interactions. So whole world of PCEs out there you can do. That's the standard slide. But what I want to show you about PCE, what makes them nice, if you have a PCE trained with a little bit of, if you take the expectation with respect to your random variable of this f hat of your PCE, and due to the basis functions having exactly the orthogonality property, you're recovering this. And if you take the variance, you're recovering that. In short, what that tells you, the moment you have your PCE expressions, you have an exact relative to the PCE. You know what the expectation and the variance of that PCE surrogate is, right? So now, those are the two quantities, and take a square root of that we need in RDO, right? So if you can train a PCE surrogate model for robust design optimization, you don't have to do Monte Carlo in that sense, right? I mean, you're trading errors at all levels, right? In Monte Carlo, you have the statistical error. You're still you're still having the right model. Here, you're dealing with so now you have the exact mean of the wrong model, right? So you have the bias in there. But people sometimes, you know, people tolerate this, and that's one nice way to do this. Okay, and you know, many layers of complexities. The problem, of course, is like you would form a PCE at a certain. Now you're in design optimization, so you have nested loops. So the fact that your PCE was good at the initial design doesn't make it any good for like the next step. I mean, it depends on how far you step into your design space, right? And you may have to retrain the PCE. Yeah. I'll show you some results later what you can do instead. But PCEs are kind of a nice way to do it because people like them because you get explicit means and variances. I also had some stuff about GPs, but I'm going to skip this because I want to show you some results. But in Gaussian processes, similar. You make assumptions about, you need to define them through means and kernels, and then you might have some hyperparameters that you want to tune, and basically in Gaussian processes, you're trying to figure out, you know, they're nice to be used for learning. You can train them very well because you're trying to find points on that curve that are trying to minimize, give you the best next point where you should train the Gaussian process by looking at that large variance. Okay. Anyways, don't want to talk much more about this, but you also have some expressions in Gaussian, once you have a Gaussian process that you can rewrite expectations and variances. They're not as nice as you had them in the PCE case, which is why people use PCEs mostly in RDO. Okay, but I really want to get, so these are two different ways of building surrogate models. So you could, of course, say, I'm just going to rely on the surrogate model, I'll eat the bias, and I'll just, you know, go sample. But there's really a better way to do this, which is the theme of this long program, which is to do it multi-fidelity. Like, can I use them and load some work into the low fidelity by still getting this accuracy? And this connects again to importance sampling. So the idea is, and we've just seen it over here, this would have been my original density P. And here in this notation, this would be Q. Okay. So now I have P over Q. If I want to compute the expectation of this, of my quantity of interest, it's the same as basically inserting 1, so a Q over Q. We now call this quantity the weight, and we call this quantity the biasing density, or importance sampling density. And so really what you do now is like you're drawing samples from this new Q, this red one, right? So I'm drawing samples from this. I count zeros and ones, or I count other things. I mean, here's for the quantity of interest. And then I have to reweight, okay? And all the multi-fidelity work kind of goes into constructing this biasing density. Like the heuristic idea here is I could take my original density and draw like a lot of samples, but I don't want to run 10,000 PIC simulations. Maybe I have a surrogate model for that. I run 10,000 simulations of a very simple surrogate, but the surrogate would tell me something's happening over here. And then I'm tuning that density to the failed samples of the surrogate only. It doesn't mean they fail in the full model, but if I trust my surrogate a little bit, you know, and then I fit a density, and that density I'm going to apply to the full order model, right? I'm going to say, the surrogate was just there to help me guide in the right direction. But once I'm in this region, I want to know from the best model I have if I'm failing or not, okay? So that's the idea of this multi-fidelity ideas, and Jonat will probably talk about this too, either today or tomorrow, maybe. Okay. Important sampling, I shouldn't talk too much about it, but you can also prove a couple of things that these estimators, and we've done this for CVAR, important sampling densities. You can show a few nice statistical things about this, but this is not the point of that. Topics that, I just left it on the slides in case someone wants to look at the slides and learn more. Topics that I did not cover, which was slightly mentioned yesterday. Control variates can also help you reduce variance for estimating mean and standard deviation. All the idea of multi-level, so if you have, that's usually nice when you have a grid associated and can you coarsen and make more fine your grid. Multi-level Monte Carlo methods, multi-fidelity is all underlying this work. You can multi-fidelity estimate the mean and the variance with nice work here. Rare events, other things, and some of the stuff that John mentioned yesterday. There's other ways to get estimators through bootstrapping and other things. So a lot of advanced stuff here, and you can dig into all of this if you need more. Questions before I show a few applications? Okay. So again, applications are not going to be in plasma physics. The first one we did, and this was about 2018, 2019, we were working on a simple experiment. This was an experiment that was set up at Purdue on a combustor. You basically, what you could do here, you had a fuel injection coming in here. This was your combustion chamber. This was modeling a rocket engine. You had your nozzle, and then you had your exhaust. The reaction that happens in here is quite sensitive to the length of this oxidizer post. And so what they did in the experiment, they did a little bit of a translating shaft where they could like make this oxidizer post mainly a little bit, they could change the length of that. And so the idea is you want to increase, the goal of the optimization was to increase combustion efficiency. That's measured by a value called C star, a characteristic exhaust velocity, while you want to also limit pressure fluctuations. So you don't want to have very wild things happening here. In a steady state, you have small pressure fluctuations. When things are getting out of control, which they call unstable, you have large pressure fluctuations. You don't want to have those. So basically, we wanted to limit the probability of a pressure fluctuation happening, which we encoded in this function, to be, I think the threshold we chose 0.5%. In 0.5% of the cases, I was allowing a pressure fluctuation larger than 13.5%. So I can deviate from my mean by 13.5% in 0.5% of the cases. So there's 2% here, right? So we set this up, we set this up. This was coming from a combustion code that was pretty expensive to run. And we had to minimize that, right? Our design variables were okay. I mean, this was a good problem. We had 4 design variables. You see where we started and where we ended. So the design did move. And we only had 3 uncertain variables, which is also nice. In 3, you're good. When it gets like 8 or 10, you have to think about a lot of other things. So these were our uncertain variables, and you just talk to the experts. They tell you, hey, the upstream pressure, you can assume this range, you can assume that range, that range. And so we now ran this. We have everything set up. This was the modeling part. A lot went into talking to the people and say, what do you actually want to limit, right? So just cooking up this function, which is not totally complicated, but just getting the right numbers and And so now we optimize this, and the way we kind of optimize this is by, one of the things that you notice, if you're in this let's say we're in a two-dimensional design space, is that if this is your design space, this is your D1 and this is your D2, you might start out here, and then your next design might be here, your next design might be here, but eventually, things cluster, and this is the optimal design. So at the first couple of steps, your system looks quite a bit different because you're operating in a different overall configuration. But as you're converging, your designs get incrementally better, so there's an opportunity to do reuse of information. Maybe you can use the PCE from the last design on the current design, right? So we did some of this stuff here. Really the main point is a lot of these things fighting for feasibility. You start out, you optimize something. This is your probability of failure threshold. You're way above, so you're not feasible. You're looking around design space. Eventually, you become feasible. Once you're feasible, you're trying to minimize the cost. That makes you infeasible again. So you see a lot of this jumping around the threshold. Eventually, you're starting to converge, so you only find feasible regions. And then we also see once we get to the region of feasibility and where we're converging, here's the reuse. We're using a lot of nearby solutions to help us out, speed the process up. That's the main thing I want to show you on this. And then a second example where we have this was on a composite joint. These are, you can't on these carbon, planes, you can't use rivets, so you're going to have to use these composites with adhesive layers. All you're trying to do is basically a tensile load test. You want to figure out if they're pretty stable. Here was a different case. We actually had 20 random inputs. We even had dependent random variables, so that needs you to think a little bit more about how you design a surrogate model. But we had 20 random variables here. We used this dimensionally decomposed generalized PCE, which allows you to account for dependent random variables. We trained a PCE, and that helped us out in the multi-fidelity stage. And we had actually two surrogate models. That's very common. Your first one could be the best model you have, finite element. The second one is a coarse finite element, or your first surrogate is a coarse finite element, and the second one is just a Kriging model or a Gaussian process or a PCE or whatever you want to have. In our case, it was a PCE with Kriging. Main thing, don't look too much at the slides, but you have a straightforward Monte Carlo simulation with the surrogate, which is biased. But you can do multi-fidelity. You can use the high fidelity or the low fidelity surrogates. And the main point is that if you use this multi-fidelity with a low fidelity surrogate to inform your important sampling densities, you're getting about a speed of about 23, and your relative error is below 1%. Okay, and we evaluated that over 30 trials of independent samples and so forth. So once again, it's a nice way to use, again, fine mesh, coarse mesh, and surrogate. It's a really nice way, and what you see here, in this model evaluation, in order to get the result, I used about 6,000 of the cheapest models, 250 of the second cheapest model, and 150 still of the best model, right? So I'm always using my best model. If I'm not using this, then I'm not going to get an unbiased estimator, right? So multi-fidelity strategies always try to use everything, but we're trying to get as much as we can to the lower fidelities. And the other thing I want to point out is here I used in this other experiment, I did not use this medium fidelity model. I used 6,000 of the cheapest models, and then I went to 400 of the most expensive models. And here I still needed quite a bit of CPU time, so I wasn't reducing my CPU time much. My error was a little bit better, but this was basically gave us the best benefit for speed up and accuracy. Okay. Good. And that's basically all I wanted to say. 3 final thoughts. The first one is you might spend a lot of time thinking about the right problem formulation, and that's a good thing. Really going back and forth if you're a mathematician or a computational scientist working with engineers trying to figure out what do you really want to design. and what can you tolerate. That will be, in my opinion, the most important thing that determines your design. You have multi-fidelity tools available. Some of them are more advanced than others. Some of them have a little bit of an entry barrier, but we're trying to make them as accessible as we can. And specifically the labs have done a fantastic job putting packages together and things that you can use and build on. So, dig into those as they are becoming more and more available. Lastly, surrogate modeling, as we have mentioned in this setting, when you design surrogate models, but they're not taking the same inputs as your high fidelity models, you're having at times a problem because you're trying to sample uncertainties, but your surrogate model is not taking that uncertainty, right? It's not reflected in it, it's not modeled in it. So in PCEs and in GPs, we naturally do that because we start from the random variables, but if you use other surrogate models, approximations, simplifications, stuff from the textbooks, they might not be, you may have to think a little bit harder how you want to use them in UQ, okay? And I think that's about it. I'll take any questions.